My talk is about online detection of changes in moment-based projections, and I added the catchy title, When to Retrain Deep Learners or Update Portfolios. And yes, the outline of my talk, but I have problems here. Okay, now it works. Yeah, so now the keyboard is on. So the agenda of my talk is, yes, first I will discuss the problem statement and its motivation, and obviously it has to do with deep learning and the problem of retraining deep learners. The method I propose and studied actually takes place in a quite general model, namely within a nonlinear vector time series model, which I will discuss in some detail with its assumptions and some examples. Then I will present the method itself, which is a QSUM related detector for online detection of a change. And then I will present the asymptotic theory, which is to some extent novel because of the more general model that studied for related detectors in the past. I will end with the application to deep learning neural networks and present some experimental support. We'll see that the approach is able yes, to limit the number of trainings of the artificial neural network to the minimal number necessary, namely, which is related, of course, to the number of changes in the data. Okay, so the motivation and aim of this talk is to have a model procedure for online detection of changes in data. And the motivation I have is indeed related to these deep learners because whatever this means, I just ignored. The training of deep learning networks, as we all know, requires massive amounts of computational resources. Yes, for example, the GPT AI models require the electricity equivalent to a small town for their training. And it is estimated that the cost for training these models is in the order of 1 million US dollars. But this problem is, of course, not only present when you want to learn such large language models, but also if you want to train other deep learning neural networks. Um, if you have massive amounts of training data which are needed by these approaches, if you want to, for example, design a classifier for a specific industrial application. These computation resources which are needed are quite prohibitive in some applications. For example, if you only have yes, a limited amount of computation resources, because the system is planned to run on small devices, for example. So think of the applications in the Internet of Things. So if you want to attach artificial intelligence, machine learning, and statistical methods to these devices, then you have to deal with these limited amounts of computational resources. But the problem is if the data distribution changes, then the network weights are no longer optimal. This means that the predictions may be outdated. This means that you apply, yes, a classifier, for example, or regression predictions using an outdated approach. Um, there are, of course, several ways to deal with that. For example, you can simply train the model on a regular basis, say each day, each week, each month or so, but this is very costly. And the basic idea is to trigger a retraining by a monitoring procedure, which triggers events which say, okay, your predictions are outdated, they are no longer valid, you should update the procedure you're using for predictions. So the framework we are considering is as follows. We assume that we are given random vectors y1 to ym, then ym plus 1, and so forth, of dimension d. And the idea is that all available data of each observation is collected in this random vector. For example, by stacking rows or rows or columns of image data and so forth. The first M observations, these are training sample of size M. And after the training sample, yes, starting at the index M plus 1, the monitoring procedure, so real life begins. There you apply, for example, your regression predictions using a method which is trained by using the training sample. Yes, we assume that we have this time context, and at each day, for example, new data arrives. In principle, your method sees this new data, but of course, you do not update your neural network each day because this is too costly. And so you use the method, the neural network, to compute your predictions. And the question is, what happens if the data distribution changes somewhat? Okay, so we assume that we have a high dimensional data, and so we reduce the dimensionality by projecting each observation onto a vector V. And the function we want to monitor, theta of the law of, say, the ith observation vector yi, is given by a quadratic form. This is a quadratic form in terms of the moment method matrix of second moments. And the idea here to monitor the matrix of second moments is that this matrix reacts to changes both in the mean and the covariance. And usually changes take place primarily in the mean and in the covariance matrix. And so we have here a tool which reacts and is sensitive to both kind of changes. But we want to see these this functional, these second moment metrics only through the projection V. So idea is relevant are only changes of this functional seen through the projection V. So, and why is this of interest? There are several problems where indeed projections matter, not the whole second moment matrix, and not a whole distribution. One example is computational finance. For example, the risk of a portfolio V of risk assets with log returns Y is given by a quadratic form in terms of the covariance matrix. And it is also well known that the Markowitz optimal portfolio depends on first and second moments. So in principle, this is exactly the situation where you can say, okay, I'm interested only in detecting a change which is relevant for my risk. So my risk is given by this quadratic form. So you should monitor this function. And now here the second application and motivation I already mentioned, and which is to some extent the second major point of my talk, is the application to deep learning. Say we have a neural network with 8 hidden layers and a linear output. So what does the neural network compute? The net computes derived features, say Z, at the last hidden layer. So this is nonlinear function of the input x. And from there, from these derived features, which are implicitly learned from the training data, the net output is computed. And usually we take a linear output function at the output layer. So that means the output is a linear combination of the derived features Z. And the prediction for new input X star is computed by putting this new input into the net, so computing the FH of X star, and then this inner product, beta prime fh of x star. So this means if we have a change of the data, so what's also now is known as a concept drift in machine learning, then the predictions are usually outdated. But actually, as we see from the formula of the predictions, they are only outdated if this inner product yes, changes. So the deep learner actually needs retraining only if the change is relevant for the projections beta prime fh of x star. So here, protection really matters. So you do not need to update necessarily your neural network if there's no change with respect to this specific projection of the derived input data. Okay, so let us come to the model and assumptions. We assume that the sequence of data vectors is governed by a nonlinear and possibly non-stationary vector time series with coordinates given by a linear nonlinear function GTJ of innovations epsilon t. And here the GTJ on measurable mappings and the epsilon t's are, yes, IID uniformly distributed random variables. And there's a lemma from Billingsley. So in probability theory, this is quite well known, but it's not so widespread, commonly known, that from simply IID uniformly distributed random variables, you can generate any distribution you like. For example, if you want to have a model for, say, p-variate innovations, as it is in a multiple linear process framework, you can derive these distributions of the p-dimensional innovations from uniformly distributed random seeds. Yes, so this is not a restriction to assume that these epsilon t's are univariate, IID uniformly distributed. So my notation for the mean vectors is mu t. Notation for the second moment matrix is mt, and the notation for the covariance matrices is sigma t. Yes, we need a weak dependence assumption which limits the amount of dependence between different time points, of course. And so that is introduced to the, so bold epsilon t. This is the, yes, current innovation and past innovations put in an infinite dimensional vector. And the second index j, this means that at index j, we replace the innovation by an independent copy of the same distribution. So we change at a certain lag t minus j, the innovation. This is the effect of this notation. And the assumption we need to have is, first we need that we have bounded moments, absolute moments of order q, at least of moment of order 4. But we will see in our results that we have a slightly better approximation rate if we have bounded moments of higher order. The second assumption is more crucial, and this is actually a uniform physical dependence assumption in the spirit of Wu, who introduced this notion and worked very intensively with it. So here we consider the impact of a change in a lag L innovation on our nonlinear time series. And this effect, this impact is measured in the LQ norm. And so the assumption is that this decreases. We have a decay condition respect to the lag. It's of the order L to the power minus beta, and beta is the dependence parameter. Okay, and it is assumed that this is uniform in the coordinates of our data. The second assumption which is needed is constrains the degree of non-stationarity by assuming that the cumulant increments yes, between different time points uh, uh, are bounded in the L4 norm, even if we cumulate them. This looks very technical and not very intuitive, but actually this holds, for example, if the mapping uh, T is mapped to the nonlinear transformations defining our nonlinear time series coordinates is smooth in a Lipschitz sense. Let us consider a more concrete example. So often the data is in forms of yes, sampled functional data. Say we have random curve data, for example, in an industrial monitoring application, we have measurement curves, they are discretized. So we sample d-random curves at equidistant time instants and assume that our data is then given by these discretized random curves. For example, here this gj of t over m and the at time t is the temperature of day j of year t, and the learning sample then consists of m years of daily temperature data. If we now assume that the function gj has a uniform Lipschitz property with respect to the first argument and uniformly in the second argument, which may be random if we plug in our innovations, but we assume that if we take the expectation, so the order 4 expectation, that then here this Lipschitz constant, which is given by a Lipschitz constant of j and some function a, h of x, is finite. Yes, and because of this Lipschitz property, because we have a discretization of the, so the grid size here is 1 over m, so this carryovers here to the L4 norm, and if you accumulate, then this remains bounded, so our assumption is fulfilled. So you may think of discretized smooth data curves which are Lipschitz, and then this assumption holds. The third assumption imposes conditions on the training sample. So usually for training and machine learning, it is assumed that the data is IID. So this is, of course, a very restrictive assumption, which, however, is usually imposed. But if you look at the applications of machine learning methods, neural networks, and if you look at the training data they use, then it's quite clear that this data is not IIT. And so here the assumptions which are here formulated for the training sample are much weaker. So of course we assume that during the training sample we have no change. So we have a stability hypothesis, and this means that our function we look at, so the quadratic form of the second moment matrix, is constant in the training sample. So it attains a constant value, say theta 0. And there's a second constraint and assumption we impose during training, namely that the non-stationarity is to some extent limited. So this assumption says that you can approximate the pseudo-covariance structure by something where you use functions j which do not depend on t. So this is behind this assumption too. So the relative error when replacing these pseudo-lag cross covariances of our real data with yes these expressions by the lag h cross covariances of g0 epsilon t is of the order 1 over n. And this assumption is basically used in order to get nicer limiting distributions. So then we get formulas in terms of Brownian motion, as we will see. Okay. The second assumption is also not very restrictive. These are long-run variance covariance matrices which arise in the asymptotics. And we need to assume that the minimal eigenvalue of these covariance matrices does not tend to zero. Okay, in practice, the V, the projection vector, may be unknown. Then you can use random projection. And this actually works quite well. But in other cases, you want to use an estimator. And so here are assumptions about these estimators. So in a high-dimensional context, people usually use sparse estimators. So if we have used a sparse estimation technology, then we assume that our estimate of the active set of coefficients of the vector which are not zero, that this is consistent. And we assume that we have a convergence rate of our estimator Vm hat. And it is assumed that the convergence rate is of the order square root of Rd over M. So the usual in the finite dimensional, low dimensional case, you would have Rd equal to 1. If you have dimension D, then you have D over M, which then typically means that D must be of smaller order than M to have consistency. And if you have sparse estimators, then actually the sparseness parameter S, which means you assume that you have only S active coordinates and you estimate them, then S takes the role of the dimension. We assume that S grows at most as square root of M. And in addition, it is needed that the square root of S times Rd grows slightly less than square root of M. And if you work in a non-sparse setting, then we need the same, actually more or less the same assumptions with S replaced by D. Then we have a constraint on the dimension, so it is not allowed that it grows faster than the square root of M. And again, we need this assumption here that the square root of D times Rd is at most of the order M to zeta, and this is zeta is smaller than 1/2. But this assumption includes the typical cases easily. And if you use a sparse estimator with a nice rate of convergence, we have available these estimators, then one can analyze that the dimension can essentially grow almost exponentially. So this is the assumption on the estimator. So now the monitoring procedure itself. So at time m plus k of the monitoring procedure, which starts right behind the training sample, we compare the current sum of the most recent k observations after some transformation of them, and we compare them to an average calculated to the training sample. So we have the training sample, and we compare something computed from the monitoring procedure with something we compute from the training sample. We had a constraint so that we look into the monitoring procedure after a small delay m times delta. So essentially we start at this observation, and here the idea is to base a decision not only on, say, 1 or 2 observations of the monitoring procedure. So we have at least m times delta observations from the monitoring procedure to have a valid decision. So we have the no change hypothesis that our quadratic form of the second moment matrix is constant all the time against the at most one change point alternative hypothesis, where it is assumed that there's a change point denoted by k star behind m plus delta, m times delta, where up to this point we have value cedar, we see the value cedar, but after the change point we have a different value. Yes. So this is the change point hypothesis testing problem we want to attack. So to detect now a change point at the case time point m plus k of the monitoring period, we consider for known v the following QSUM type detector, where we accumulate our evidence in terms of v prime sy v, where Si is the outer product of our observational vector yi. And we compare it because these are here, this is the sum of k terms, and we compare it by k times the associated average of the training period. So this is a QSUM approach. If v is unknown, then we simply replace v by its estimator vm hat. So this is then QM and K. And we compare this QSUM statistic with a multiple of a boundary function. This is the class of boundary function which has been proposed in related previous work. It's quite well known that this boundary function works relatively well. If you expect that the change is early, that you have an early change, you should select the gamma closer to 1/2. Otherwise, you can choose a smaller value of gamma. The value gamma equal to 1/2 is not allowed because then the resulting expression has no well-defined limit. So we signal a change and reject the null hypothesis of no change and conclude in favor of a change of the data distribution themes who are functional. If for the first time our QSUM statistics exceeds a certain multiple of our boundary function, and here we introduce a certain estimator of the asymptotic variance of the scaled partial sums of the terms we are basically looking at, in order to get an overall statistic which is scale invariant and leads to a well-defined limiting distribution in terms of Brownian motion. So this means we have a well-defined stopping time. We can formulate the procedure in terms of this stopping time. We also have a related closed-end procedure. So this procedure monitors the sequence forever. And in case that we say, okay, we introduce a time horizon, which we express as a multiple of the sample size of our training sample, then we consider this stopping time, which stops latest at the time horizon. Otherwise, the construction is the same. And in this case, one has more freedom to choose a boundary function, actually. If you want to apply the whole procedure to a regression setting, we can do this. For example, let us assume that we have this regression model. We regress our a response variable zt onto our data vectors yt. So v is the true regression vector of regression coefficients, and we add an error term. Then we may consider the detector based on residuals of this regression. So we compute the regression residuals, square them. Then we see that we have this expression, of course. And actually here we see that as the crucial part of these squared residuals, this quadratic form appears, which is the essential part of our detector. And in principle, the approximations I want to present in the next section carry over to the setting, and this is the most difficult part, so we will focus on this critical part of these regression residuals. So the asymptotic theory relies on these sequential Gaussian approximations. This parameter psi x is more or less the idealized approximation rate we can achieve. If the dependence parameter beta is relatively small, we have this simple expression, and you can almost reach the approximation rate 1 over beta for the standardized procedures. And if we have high, higher, so less dependence, this means beta is large, then we have here an expression where only Q enters. And Q is the number of moments we have available. So we can become better if we have more moments and we have less dependence. And under the assumptions imposed on our model, we can approximate partial sums of the quadratic forms centered at the expectations and standardize correctly by standard Brownian motion. Uniform over k, and this is of the order m to the power 1 over nu, and nu is essentially given, so it's larger 2 and essentially given in terms of the psi expression. And we also can replace here the standardization, which here has to be done for each term, by standardization which is uniform in I. And then we get a much easier expression. And actually, this guy here can also be estimated if you wish to do this. If in addition, we assume that we have an estimator of the projection vector, then under the stated assumptions, we can replace V by its estimator and still achieve these Gaussian approximations. Now, these Gaussian approximations are indeed generalizations of the central limit theorem. So essentially, they apply the central limit theorem, but they are more general, and especially they provide us with an approximation rate. To summarize, the approximation rate is controlled by beta if beta is small, beta dependence parameter. The rate is controlled by moments q if beta is large. And the best rate we can achieve here is 1 over 6. This is achieved for the case that beta is bigger than 3 and the moments tend to infinity. So if you have, for example, bounded data. This is worse than the best approximation rate, which is known since a couple of years. There's a breakthrough paper from Eldan. And in the case of IID data vectors, the best achievable rate is 1/2. However, we do not achieve this optimal rate of approximation here, but our model is much more general. So we assume a time series model, non-stationary, so we have much weaker conditions, and there it is not possible to get the optimal rate of approximation, at least not under these very weak assumptions. So we can now derive the detector asymptotics under the null hypothesis. Of course, we want to select the parameter c, which says is the multiple of our boundary function, in such a way that the probability that our detector gives a signal, although there's no change, is controlled by an error probability alpha. And the first result here, this theorem tells us that we have this weak convergence. So the limit of this probability distribution here of this sub-detector statistic converges to the corresponding subfunctional of Brownian motion divided by t over gamma. For the case delta equal to 0, this distribution is well known and is known from the literature, and there are no explicit formulas for this limiting distribution, but you can simulate the quantiles and can use them as critical values. So for delta small, one certainly can rely on these tables, and for delta larger, one can easily simulate this distribution to get concrete values for the C. But here's more. So actually I worked out the asymptotic theory under local functional alternatives. And here it is assumed that we have a function delta. And this delta function tells us the shape of our functional which we monitor. So this quadratic form of the second moment matrix after the change point. So we model the local functional alternatives in terms of our moment functional which we monitor. And delta must be an integrable function. Right continues at 0, and at 0 it is not equal to 0, so that there's really a jump, a change point at the location k star. And then this model is much more general than the usual jump point alternatives, where it is simply assumed that you have a change point and then again the level is constant. So here you can model what you want by this delta function and then analyze how the procedure behaves. This is a local alternative functional model because here it is divided by square root of n. So if the training sample gets larger, then it's assumed that we make the problem to detect this functional alternative, make this problem harder for the procedure. And this is the right scaling to obtain formulas which are not degenerated. And for this part of the theory, it is assumed that the change point is located asymptotically at a certain fraction relative to the sample size m. Okay, and under these assumptions, one can derive the following reconvergence result, so that our detector overall statistic converges in distribution to this functional. And here we see the impact of the delta function. So the impact is it corresponds, it induces a drift term in the asymptotic distribution, which starts right after the change point and then cumulates the delta function. So the cumulated impact of the delta function gives here the drift function. And here B1 and B2 are two independent standard Brownian motions. This looks different than the formula before, but essentially this is because here's a finite samples time horizon which we consider, and if capital T is equal to infinity and if delta is 0, then one can show that this expression here is equal distribution to this expression here. Okay, so if we want to estimate projections, then in many cases, the optimal projection depends on the covariance matrix or on the precision matrix. And because of this, here's a result about threshold estimators of the covariance matrix. We are in a high-dimensional context. There's this interesting to use thresholding estimators in order to get reasonable approximation rates. Bickel and Levine introduced this uniformity class of covariance matrices. But actually it turns out that the theoretical results do not only apply to covariance estimators, to the sample covariance estimator. Actually, you can use them for any estimator of a matrix which is symmetric and is within this uniformity class, which is a kind of sparseness assumption. And as naught here is the sparsity parameter. Yes, and this class is constructed in such a way that the row sums are bounded if you take the elements to the rth power, but R must be a little bit less than 1, so these are not really the row sums, but almost. And the minimal eigenvalue must be bounded away from 0. And then all matrices within this class have a spectrum which is contained in a compact interval which is bounded away from the origin. And the threshold estimator is then obtained by thresholding the estimator for sigma entry-wise. So we only take these entries which are greater or equal than t in absolute value. And t is the threshold parameter here. So this operator defined by this equation here is the thresholding operator. But one may also apply soft thresholding. And here we also null entries which are small in magnitude than t and shrink them to 0 otherwise. And actually any operator st is called a soft thresholding estimator if he satisfies these conditions. So it is less or equal than to the modulus of x. It is 0 if x is less than or equal than our threshold t, and it is not too far away from the identity. Important special cases are, of course, hard thresholding. The Lassus-soft thresholding, which is very commonly applied, is also a special case of this thresholding class of thresholding operators. The scat thresholding is between hard thresholding, and Lassus thresholding is also contained in this class. And so the next two results are extensions of the work of Bickel and Leviner. And this first result is actually an estimate of the operator norm of the soft thresholded matrix gamma. So we take any matrix gamma, we apply the soft thresholding estimator, and compare the result with the truth we want to estimate. And the difference, the operator norm of the difference, can be bounded by this expression. And this is a purely algebraic result. So nothing enters. So this is it holds for any matrix gamma and for any matrix sigma from our uniformity class. And we see that we bound it in terms of parameters defined by the uniformity class, in terms of the maximum norm between gamma and sigma, and the number of elements which are greater than some almost the threshold. And here again, some two terms which depend essentially on the uniformity class parameter S naught, defining the degree of sparseness of the underlying sigma. Yes, and using this basic, elementary, but crucial inequality, one can show that under our very general vector time series model, thresholding the sample covariance matrix allows us to estimate the true covariance matrix consistently, and we get the same result as in the papers of Bickel and Leviner, but these results are for IID vector data and not for nonlinear and not possibly non-stationary vector type series. And from this result, by using known elementary inequality between the operator norm and the operator norm of an inverse matrix, one also gets consistency of the thresholded precision matrix. Okay, so now let us come to the application to deep neural networks, which I promised. So let us take a look at how a deep neural network works. So with a d-dimensional input x, and say we generate a univariate output y. These nets are recursively defined in the following way. So the inputs are connected to neurons of the first hidden layer. The connection weights are put into this weight matrix W1. And then we apply element-wise to this resulting vector a nonlinear, possibly nonlinear activation function. Then this is processed into the next layer. And so the next hidden layers are defined recursively. We take the output of the previous hidden layer, apply our weighting matrix Wj, which means these are the connection weights to the neurons of the jth hidden layer, and then apply again the activation function. And at the output layer, we use a linear activation function. So the output of the net is given by a linear combination beta prime applied to fhx and fhx. This is the output computed of the last hidden layer. So in our prediction, which we then use, is given by beta m hat prime fh of x, and beta m hat are the trained weights learned from the training vectors, the trained weights of the output layer, of course. Okay, and the regression model we then formulate for response yt tilde before possible change point k star is as follows. So we assume that there are true parameters beta 0 and theta 0. So theta 0 are all weights of the neural net we need for the hidden layers. And beta naught are the parameters of the linear output layer. And we add error term ET, and if we fit this regression model by least squares, this is what is really done by in practice in the machine learning community when training such a deep learning network. They apply backpropagation, or what is in a certain sense, the state-of-the-art algorithm in practice. This is Adam. Also played with Adam, so it's really a great algorithm. By the way, the original papers, the proof is not complete, and there's an improvement from German colleagues who corrected the convergence proof of the Adam algorithm. You find it in the internet. Yes, but if you apply backpropagation or stochastic gradient descent or Adam or whatever, these algorithms minimize the least squares loss in the training sample, and this corresponds to such a regression model where we assume that we have here zero mean noise process and a regression model of this type. Okay, so let us denote by Z1 of beta the output of the last hidden layer. Then by formulating the normal equations, so the necessary conditions for a minimum, we see that we get these normal equations for the output layer. These normal equations of the output layers, this is simply a system of linear equations. So we have an explicit representation for the optimal parameters at the output level layer. Yes. So this is the usual formula you have for least squares regression. And the sample version, our estimate, of course, solves the corresponding sample normal equations. So we have these equations here for our estimates on the level of the estimates. It's the empirical normal equation for the output layer, which is the linear equation. And from using this fact, one can show under regularity assumptions, assuming that the dimension of the neural network is held fixed, that we have a convergence rate of the convergence rate order 1 over square root of m. So we have the usual rate of convergence for the estimator. Essentially, for neural networks, that such results hold true is well known from the 1990s. But there are nowadays more elegant theories which gives us these results. And in the paper of my talk, which you find on arXiv, there's more information also about this. So we see that the optimal weights, and we have a formula for them, encode the second moment structure of the last hidden layer and its covariances with the responses. This is encoded into the optimal weights of the output layer. And our estimate approximates this up to an error. Okay, so what are therefore the proposed detectors? We can formulate a projection detector. We apply it to the input vectors of the monitoring procedure. This means we apply the detector studied and discussed with the following settings. So ym plus 1 is defined as the output of the last hidden layer applied to the corresponding input vectors using the trained weights. And the estimated projection vector is the least squares estimate of the weights of the linear output layer. In addition, one should run a residuals detector. This is applied to regression residuals. So here we set ym plus 1 equal to the residual or the squared residuals, and again use the estimated, the trained weights of the linear output layer as the projection vector. So how does this work in practice? Here's experimental support using synthetic simulated data. And the simulation model here is as follows. So for the first 2,000 observations, we have this black sine curve, cosine curve. Then between 2000 and 4000, so at 2000 is the first change point where the data distribution changes. This is implemented by change of the regressor variable, which has now a different distribution. And then we have a further change point where the frequency changes. So then after the second change point, we have this red curve. Yes, so we have 2 change points, and this means we need to train our neural network right at the beginning. This is number 1. Then after the first change point, 2, and after the second change point. So we need to train the data 3 times. This is the minimal number of trainings required. So I applied for this hypothetical data and toy data example. I used a 3-layer network with ReLU activations and linear output layer. So 4 to 1 are the number of neurons. For training, Adam was used with 100 epochs, batch size 32, and a validation split of 2.0. The first 1,000 training examples were used in order to train initially the network, and then the detectors were applied to the predictions and rolled over after giving a signal. So here you see the results. You see here to the left the detector statistic. This is the projection detector, and here you see the boundary function in red. This is the detector statistic in black, and you see that after the change point, it increases very rapidly and quite quickly crosses the boundary function and gives the signal to retrain the net. Then the net is retrained and the procedure is rolled over. The second change point does not really change the data distribution, but it changes the regression coefficients. So here no signal is given. So you see that here the detector statistic stays more or less stationary. But a second detector then kicks in. So the regression detector is able to detect this change of the regression coefficients. These are the weights at the output layer. And here this detector does not really work, but this detector works. And here after 4,000, it increases very rapidly again and then crosses the threshold and gives the signal. And you see that the method reacts quickly and really triggers when we need to retrain our neural network. And you see that even if then we run the predictions and use the neural network for predictions for a long time, there are no false signals. So in this synthetic data. So let me conclude. I discussed and proposed online real-time detectors for changes in projected second moments. Um, uh, the theory works for nonlinear time series models, including discretely sampled functional data. The data may be non-stationary, even under the null hypothesis of no change, and even in the training data. So we have very weak assumptions on the training data, going beyond the classical IID assumption or the assumption of stationarity. We have valid asymptotic theory under the null hypothesis, but also under local functional alternatives. And we discussed application to deep learning and proposed an algorithm which really achieves minimal number of training rounds. So I really think that if this approach is applied in practice, it may contribute to a considerable, substantial decrease of the required computation resources for machine learning. And this really matters if we think of the costs in terms of money and power, so electricity, which is needed to train artificial intelligence neural networks on these large scales, which they are used today. Not only in these large language models. Perhaps this is not really implementable for large language models because of their nature. I don't know. We would just need to study this in greater detail. But I think here this is directly applicable to many machine learning approaches which use deep learners for specific problems in regression settings. Okay, let me conclude here some references. And you find the material I presented, so the corresponding paper, the preprint version on archive. Thank you very much. I have to